Very good morning, students. So this is a continuation of my previous lecture on microbial and bioprocess technology. We already completed all the different types of fermenters and information related to the basic concept of bioprocess technology and everything. And maybe we can have a look of all the previous slides before going to the solid state fermentation process. Yeah, this is the first slide. So what is the fermenter? So what is the difference between fermenter and bioprocess technology related processes, and the difference between the fermenter and the bioreactor, and different parameters related to biomass concentration, soil condition, effective agitation, heat removal, nutrient supply, and all the components, and three different groups of bioreactor. So we already had this one. Do you remember this one? Non-stirred, non-aerated, non-stirred, aerated, and stirred and aerated systems. So this is next slide, and we have two different types of fermenters: submerged fermentation process and solid state fermentation process. So this is the ratio, that is the different the distribution of types of fermentation. So that is non-stirred and non-aerated 76%, non-stirred and aerated 11%, stirred and aerated 13%. And this is the overall outline of fermenter or bioreactor. And this is an example of a complete setup of bioprocess. So this is the first part. Okay, till this one, this is called as upstream, using the microorganism and optimizing the culture condition and the preparation of media and pouring the media into the fermenter, preparation of inoculum and addition of inoculum, and maintaining all the pH, temperature and aeration, agitation, everything for the production. And after the production, once the product is ready, the next process is going to start. Okay, that is downstream process. So this downstream process is very important because more complicated when compared to the upstream, because upstream you need only the basic knowledge of microbiology and how to maintain the strain, and how to maintain a pure culture, how to maintain an inoculum development, and the basic sterilization of fermenter and assembly of fermenter or bioreactor, that's all. And operation like maintaining the oxygen, DO level, pH, antifoam, and everything. Okay, this is not done by you. Okay, that is done by the software, because so most of the fermenters or bioreactors are fully automated. Once you feed the components, what are the components you need? That is dissolved oxygen, pH, agitation, aeration, and everything. Automatically, that will control. So this is very simple when compared to the downstream process. And downstream, this is a major component and more complex area, and you need more knowledge about proteins and all the primary metabolites, secondary metabolites, especially the solvent extraction and chromatography techniques, the basics of buffer preparation, and the maintaining uh, the sterility, okay, within the downstream processing area. So all these components are very important and play a vital role, okay, in the downstream process segment. So this DSP is there are two components. One is in situ DSP and ex situ DSP. In situ means so within the fermentation process, okay, that is within the component itself. So this is performed, and ex situ means, okay, we are going to get the fermented product out and to the different area, and to make all the components will be available for downstream process, and going to each and every stage of downstream, and finally we'll get the finished product. So mostly all the industries, okay, they have in situ DSP, because that is most cost effective, and also the sterility problems, okay, can be avoided, and the main thing is, okay, more expensive. At the same time, the Exito DSP is little expensive because you need the different areas for different the process of downstream processing. So here the cell disruption or cell separation and centrifugation and filtration, okay, this is one area because you have to clarify the component. You have to separate the cells, that is biomass, so from the culture filtrate, and you have to remove all the cells, and all the harvested cells, okay, can be used for either waste or otherwise. Okay, if you need biomass, maybe if your the product of interest is cells, maybe you can have this one. And this medium, okay, that means the supernatant, okay, used for further process of extracellular product purification. That means if your product is extracellular and this concentration of the extracellular product, okay, that means culture filtrate can be further concentrated, and this one, okay, further processed for purification process. So the harvested cells, there are two different types, okay, the intracellular or periplasmic product, because the cells having the extracellular component, okay, that is purely this culture filtrate, we are going to get it as a supernatant. If it is a cell, most of the components may be in the extracellular, so that is very easy for the downstream. If your product is intracellular, that means either within the cell wall or cell membrane, and if it is between the cell membrane and cell wall, that's called as periplasmic space. So you need lot of procedures, okay, for this one, that is cell disruption and cell wall lysis and the complete lysis of cell. So based on your product of interest and what is the location, that is localization of the product, and you have to process the different stages. So this is a very complex area, and you need more technical and also the biochemical knowledge to carry out all the stages in a very careful manner. And finally, so this product purification, okay, can be performed by dialysis, precipitation, and partition chromatography, and different steps of chromatography techniques, including ion exchange, affinity, gel filtration, hydrophobic chromatography, and everything. And nowadays, okay, we are using ultrafiltration methods and distillation if it is needed. Okay, that's distillation also. And finally, the finishing. After purification, the finishing process is the crystallization, drying, lyophilization, and sterile filtration and packaging, because you cannot sell the product, okay, in a liquid or otherwise, okay, directly from the downstream processing, because that has to be concentrated as a powder or otherwise stabilized with the stabilizing agents if it is a protein, and if possible, okay, you can crystallize the protein if it is needed. And okay, this packaging, the sterile packaging by using gamma irradiation method, okay, for packaging, and the preservation in the cold atmosphere, okay, till the transport completed, and all these components are needed. The knowledge of the components are much more needed, okay, for the bioprocess technician or the biotechnologist. So these are all the overall process, okay, and these two components are very important in the bioprocess, and we are going to study all the components from A to Z. Shall I go to the next slide? Yeah. These are the different types of fermenters. This is also completed, and all the different types: stirred tank bioreactor, airlift pressure bioreactor, and loop bioreactor, immobilized system, fluidized bed, trickle bed, fed batch mixed bioreactor, and batch mixed bioreactor. All the components we already had, and these are the different types of bioreactors. Airlift. So this airlift is nothing but, okay, the only the air is used to mix the components, okay, within the fermentation process. And yeah, so this one, the air is passed, okay, from the bottom. It is not like a sparger, okay, it is like a sparger, but the pores are not there, okay. This is the very minute part is there, okay, that is the inlet of air, okay, through the sparger, and this one will be going to the top, and there is a cyclic movement of the fluidics, okay, may be happening, okay. This will mix all the components within the fermenter. So this is a very simple one, and without need of a much more very complex pumping process or something. And to facilitate the air supply, okay, we can use a pump or a compressor with pump, okay, that can be used. So this is more energy efficient process. And stirred tank bioreactors, that is, stirring is needed mechanically by using a the component, okay, within the fermenter is called as there are two components, okay, involved in mixing. The first one is agitation by, okay, this that is Ruston impeller, marine impeller, and paddle impellers. Okay, there are three different types of impellers are there. The impellers are the major components used for mixing the media, okay, within the fermentation process. And another one is there, okay, to focus all the components into the center, okay, that is called as baffles. Baffle is also facilitate the mixing process with the help of impeller. Once impeller is there, okay, automatically the baffles has to be used, or otherwise, okay, this the rotation of all the components, all the liquid components will form a cyclic movement of liquid, and the mixing process, okay, will not happen much. So this is stir tank bioreactor, and this is an example. We already had an example, and this is the next type, bubble column fermenter. Bubble column means through the sparger, okay, maybe we can pass a mild one, okay, without much pressure, okay, we can pass the air from the bottom. So this air sparger will form a minute bubbles, and this will go to the top. So here, because this one does not need, okay, much more energy for this bioprocess, and most of the things, okay, this can be used for the baker's yeast production and beer or vinegar production. And bubble column fermenters are used because it is more energy efficient and more economical also. In designing of bioreactor, the height and height of the liquid to tank diameter, okay, that means the height is to diameter ratio, that is either 2 is to 1. A common ratio is about 3 is to 1. In baker's yeast production, okay, that is 6 is to 1. Okay, then this is a major component. This may be asked in the section A. And airlift bioreactor. Airlift bioreactor we already had, and these are the different subtypes of airlift bioreactor. There is internal loop vessels, draft tubes, and external loop or outer loop. Okay. Next, coming to the very important component, that is immobilized cell bioreactor. So this type is more sophisticated, and you need more the knowledge of more biomolecules, how to immobilize the biomolecule or cells, okay, on the surface of resins. And this need, okay, more technical knowledge and more technical expertise, okay, to carry out all the immobilization process. Usually enzymes or viable cells or plant cells or animal cells can be immobilized. All the four different types, either enzymes, viable cells, usually bacterial cells, plant cells, and animal cells can be immobilized to the resins, the synthetic component. It can be divided into stir tank reactor, fixed bed bioreactor, and a fluidized bed bioreactor. These also can be combined or modified. The choice of the reactor design for ICB, it could be depends on mass transfer requirement, oxygen supply, and gas removal. And the particle characteristics are in stirred tank reactor, damage to the particle is greater than packed bed bioreactor. And the kinetic considerations are that means how much products are formed, okay, from the substrate. If it is very fast, for example, some of the enzymes can produce its own products, okay, within a very short span. That means maybe 27,000 substrates converted into 27,000 products, okay, within a second. So this is the fastest enzyme, that is cholinesterase. And if it is like that, okay, you have to provide, okay, more amount of substrates to the enzyme and the removal of the product, that is substrates to the product enzyme, and also removal of the products. So the methods of immobilization, okay, it depends on the active immobilization and the passive immobilization. The cross-linking and covalent linking and entrapment of the gels are active immobilization categories, and the passive immobilization, adsorption and colonization. Active means that is commonly used for enzyme immobilization, and the passive immobilization means not direct, okay, this is not specific. That means only adsorption. Only the cells will adhere to the synthetic components, like that. Okay, nowadays The active immobilization is also used for the cells, the plant cells and the animal cells also. And next slide is, so this is the example of immobilized bioreactor. The first one is stirred tank immobilized cell bioreactors. Okay. So this one you can see there is a shaft is there that is passing, okay, or the liquid components, okay, into the feed. So this is a feed, okay, that is inlet and this is outlet, and this is the air. The air is optional, and so this is the rotation. Rotation means a simple rotation or a gentle rotation of, okay, this one stirred tank bioreactor with anchor impeller. With anchor impeller means, okay, that will not imply, okay, much mechanical force, okay, on that. So the immobilized components are placed in a liquid, that is bufferized conditions, and a mild agitation, okay, can be followed, okay, to mix the components to facilitate the supply of substrate and recovery of the products. So this is a very common one, stirred tank bioreactor with anchor impeller. The second type is stirred tank bioreactor with the cells, okay, in a porous mesh. So porous mesh means, okay, there is a mesh, okay, there is usually the Teflon mesh is used because Teflon is a component, is a polymer that is not reacting, okay, with any chemical substance, that is non-reactive. That is why we are using Teflon, okay, in our kitchen utensils as a non-stick. Usually, okay, that is not recommended because that will cause all okay, adverse reactions, okay, some of the reaction may be cancer, okay. And nowadays we are using, unfortunately, but this Teflon having a potential use, okay, in the bioprocess, you can use the Teflon mesh to hold all of your okay, the immobilized cells, okay, within that, and you can provide, okay, the nutrients, and you can get all the products outside. So nothing is going to be disturbed, and in the bottom, okay, there is a impeller. So the bottom you can mix the components to facilitate the feed, the complete mixing of the feed and also the outlet. Okay. And third type is rotating biological contractor. Okay, there's a feed is there is a inside, there is a cylinder is there, okay, inside there is a drum, the rotating drum, and within the drum we can pour all the immobilized cells or immobilized enzymes, okay, within that, and you can feed the components, okay, within this, and automatically due to the rotation of, okay, this one, it will get the nutrients, or otherwise it will get, okay, the substrates and all the buffering agents, and automatically it will produce the products. And this is the inlet of the feed and this is the effluent, so we will get all the components. So next one is advantages of immobilized cell bioreactor. That means what is advantage when compared to the stirred tank, or also, okay, this submerged fermentation and solid state fermentation. So this is so-called, okay, submerged fermentation only, but within submerged fermentation, okay, this is more dominant. Okay, that means there is no loss of cells, first of all, okay, no need to provide, okay, all the very expensive components, okay, as a media, and maybe the economics, the bioprocess economics is very high when compared to all the different types. We can see one by one. The application is multi-step enzyme reaction, okay, may be possible. The enzyme activity yield on immobilization is very high. Okay, this is the first point, because enzyme activity should be very high, because whatever you have in your enzyme, okay, that enzyme has to convert all the substrate into product. For example, so within the column, if you are loading, okay, all the isomerase enzyme, okay, this glucose isomerase enzyme, okay, you need the product fructose. If you're passing the glucose solution on the top, in the bottom you can get fructose, because you are adding the enzyme, okay, in the solution. The enzyme, okay, maybe act on the glucose and converting glucose into fructose. That is over. Okay, once for a time, maybe after a particular duration, the enzyme will be lost, and you have to remove the components. So here the immobilization, you can entrap, or otherwise you can form an immobilized enzyme, okay, that is glucose isomerase enzyme, and this enzyme is packed, okay, in a bed, and you can pour the component, that is a glucose solution, on the top with the bufferized medium, and if it is coming out as a fructose. So the enzyme activity yield is very high when compared to the normal process, and operation stability is very high. Okay, and stability means this is stable. Okay, because if you are providing the air conditioned room or otherwise a cold room with the normal the temperature maintenance and also maintaining the pH, everything is perfect, means okay, you can produce the products in a constant manner. The stability is very high in compared to all the different types of fermentation process. The operations for enzyme extraction and also purification are unnecessary, because you don't need the extraction of enzyme. You don't need, okay, this purification, because water, for example, okay, I told just now, okay, the conversion of glucose into fructose, if you have a column bed and that is the filled with glucose isomerase enzyme, and you are passing the glucose, and you will get the fructose, and no need to separate the enzyme, because enzyme is intact. Just you have to regenerate that enzyme after a particular time. Okay, if you are maintaining the proper temperature, that is a cold temperature, at the same time if you are maintaining the pH and the porosity of the packed material, if it is really good, so no need to change the, or otherwise no need to change the cartridges and all. Okay, and the operation cost is less when compared to any other product, and enzyme extraction and purifications are unnecessary. You will get the product directly, and high cell densities can be employed. So you can keep lot of dense material. Okay, that means so if it is an immobilized pack, means okay, that is having a lot of enzyme, so no need to maybe dilute the enzyme. So all the enzymes are completely immobilized, okay, in a bead, and that is more concentrated. The cell density is very high. The cell densities and enzyme activities can be expected to be maintained over a longer period of operation. This can be operated for a longer period, and the products can be easily removed from immobilized cells. And the product recovery is very easy. Just now I said, okay, we can get the fructose directly from the bed, column bed. And products can be easily removed from the immobilized cells, and immobilized cells appear to be less susceptible for microbial contamination. If you are maintaining the cartridge, and if you are maintaining the input, okay, the inlet, the feed, okay, with buffer, and also okay, all the components and everything is right, so no need of bothering about okay anything, because okay, this one is okay, for a longer period you can run the show. That means no need of changing the cartridge, no need of changing the immobilized cells. At the same time, okay, for all the processes, okay, it may have the positive and also negative. So we can see the negative aspects of immobilized cell bioreactor. Uh, the first one is the cell membrane itself may serve as a diffusion barrier. So there is a limitation for the diffusion process. For example, if you want to give the media components to the cells, okay, if it is an immobilized cell, and if you want to give the protein component to the media, okay, this is the protein component of the media to the cells, so this diffusion process may be hindered, okay, if it is a larger protein molecule. So this may be the disadvantage, and the contamination by the cells leaking out from the carriers may occur. Sometimes, okay, if the cells are the completely entrapped or otherwise immobilized, some maybe the leakage, okay, from the immobilization may happen, okay, due to the temperature or otherwise, okay, any the change in the pH or osmolality, or otherwise maybe the salt bridge, the the dissolution of okay, the ionic bridges and all. So sometimes, okay, the cells may be liberated from the immobilized component, so that may contaminate your product. Okay, and next one is the physiological state of the microorganism cannot be controlled. The physiological state means no, we can hold the microorganism, okay, for the particular extent, maybe because the microorganism is dividing, okay, the binary, the division may happen, okay, and we have the limitation, okay, for a period we can maintain the gel beads and all, and after that the gel bead will burst because due to the multiplication of microorganisms. So this immobilized bioreactor can be suitable for enzyme immobilization, that is 100%. And only one thing, okay, you have to maintain the sterility and maintaining the pH and ionic strength and everything. That's all. And if it is a cell based bioreactor, immobilized cell, And there is a limitation for physiological state of the microorganism because the cells will started dividing. So once if it is started dividing and it may be detached, okay, from the immobilized component, that may contaminate the whole process. So these are all the parameters related to immobilized fermentation process. Next one is solid state fermentation. I can stop with this, and the next slide, okay, from that next slide, okay, we can have the different video. Okay, I hope everybody understanding the concept of fermentation process. I'll start, okay, with this slide, okay, so